Hello, welcome to this tutorial video where we're going to make a particle system in JavaScript using the P5 library. Okay, so did I say JavaScript? Yeah, I did say JavaScript. Okay, so I'm going to do this from CodePen, which means that most people watching can just code along if you want to. You could use a code editor like brackets or even a text file if you wanted to code, and then it's just going to run in a browser. If you go to CodePen, that will all happen automatically, and it's very easy to connect the library that you need. So I'm going to show you everything. So all you have to do is go to codepen.io, and then near the top you'll be able to find this create button, and you just have to go there and then create a new pen, and then you'll have a screen that looks similar to mine, like this. There we go. So I'm going to change the title by clicking that little pencil, and we're going to make like a physics system. There we go. Right. So I like to have my code on the left hand side. So I'm going to click on settings. No, I'm not. I'm going to click on change view, and then I'm going to click on this panel here so that we can put the JavaScript on the left hand side. And then here, actually I'm going to have that update automatically by going to behavior, putting enabled on, and that means, I don't know if you saw it, but there was a little button here that said run, but now when I put some code in here, the code will, or the browser will automatically run the code whenever I make a change, and that's the default setting. Right, so first we need to attach the P5 library. So if we go to settings and we go to JavaScript, and then in here I'm going to put p5.js, and then it should find the P5.js library. There we go. Save and close that. Now we can use all the P5.js functions like setup, draw, ellipse, all that kind of stuff that we need. So what we're basically going to do is create a class of particle objects and then do some interesting things with them, like we could have them follow the mouse and create kind of gravity. You could create systems that look like the nuclei of atoms and have clouds of electrons around them and things like that. But it's up to you what you make with it. Okay, so is my zoom big enough? I'm going to go that big so you can see the code. So first we need a setup function, or a stub function. There we go. Function setup. And this is where the P5 library will start synchronously, line by line, running your code, for a better word. Right, so to create a canvas, we use a P5 function, create canvas, and then you tell the canvas how big you want to be. So I'm just going to go 400 by 400, which is fairly small, and I'm just going to refresh. There we go. Can't quite see my entire canvas. Anyway, to be able to see the canvas, because it's just matching the white of the browser background, I'm going to write background, and then in here we put three parameters, red, green and blue. So I'm going to go for pink, which is a little bit of red, no green, and approximately the same amount of blue. So I've got a pink there. Okay, so things are working. Right, if things aren't working for you at the moment, just go and check the settings and make sure you have connected that P5.js library. Or check out my other videos. There's another way to do it where you could check it, you could connect it via the HTML. If you're a beginner and not sure how to do that, maybe have a look through my videos, or obviously anyone else's videos, and you'll find it. Right, so we want to create, basically up here, we want to be able to say something like, we want to say, make me a new particle. Make a new particle. But to go and do that, we need to have like a particle object. So we're going to write that ourselves using the class keyword. So class means we're going to define, or like write the recipe for how to make this kind of object. And I'm just going to call it I'll call it a dot. So we're going to make a dot object because it will look like a dot on the screen, and dot is nice and short. Okay, so then you create the body of your class. So everything about the class will fit inside the curly braces. It's a bit like a function. And then our dot object will have a constructor. And this constructor function will be run automatically when you create a new dot. So in fact, now we can say, let's say we create global variable test dot. There we go. So we've got a variable called test dot, and now we can say test dot equals, and we just put the name of our class, the kind of object that we want, or rather the type of object we want. But because it's a type that we've made, we have to use the new keyword, and that just tells JavaScript to go and find an object that we've made. So new dot and brackets afterwards. Okay, so we've actually put a new dot inside the test dot. At the moment, it can't do anything. It's really empty. It's got nothing in there. So let's give it some member variables. Now, the basic thing is it needs a location in 2D space. And the kinds of equations we're going to do to create gravity and things like that are going to have, well, we're going to need like vectors. Vectors are easy to work with. So we're going to say this dot, that means a variable that belongs to this kind of object, this dot pos, and that's going to mean position equals, and now we're going to create a vector, and we can just put 0, 0. There we go, 0, 0. So create vector, I just need to say, is a P5 function that is not native to JavaScript. It's not going to be in vanilla JavaScript, but P5 allows you to create a vector that simply. And it's just a position vector. It's just like a variable that holds 2 values. So it's just like having like a tiny array, really. And secretly it has 3 values. It's got position.x, position.y, and position.z. And by default they'll be called that. To get hold of this first value, we'd write position.x. and so on. We don't have to worry about that. And by the way, if you just put it like that, it will set to 0, 0 but by default. I've just put it like this to make everything clear. So we want like a physics engine, a physics system going. So we're going to use Euler integration, which is just a fancy way of saying we're going to add the velocity to our position. So if we've got a higher velocity, the position is going to move a lot more each frame. And we're going to make velocities change, we're going to add an acceleration. And all of those are going to be stored in vectors. So very simply, we're going to say our velocity equals create vector 0, 0. And then this dot ACC for acceleration equals create vector 0, 0, which should make sense from physics, since forces are accelerations. Right, like gravity is an acceleration. What is it, meters per second, something like that. Right. Okay. Right. Let's now add a function. So we've got the member variables for our test dot. It's got a position, it's got a velocity, and it's got an acceleration, but even if we change those, we wouldn't be able to see it. So we've got to have a function, a member function, inside this class recipe that tells it how to render to the screen. So in fact, let's call it render. I like to call it render. So you don't write function, you just write render, and then in the same way as you would have a function, your brackets for parameters, if you want any in there, and then the curly brackets for the body. And then I'm going to say ellipse, which is a P5 function to draw an ellipse, which is just a circle, but you can squeeze the circle or stretch it that way. So ellipse, and then it wants to be positioned according to this first vector, our position vector. So to do that, we're going to write this dot pos dot x. Remember that dot x gives us the first value in this position vector, and then we're going to say this dot pos dot y. So that's told the ellipse where to draw, and now we have to tell it how large to be. So by default, let's just put 10 by 10. So it's going to be 10 across and 10 down. Okay, so now we can draw our test dot. So let's, in setup, after we've created our test dot, let's write test dot render, and let's see if it appears. Can you guess where it'll appear? Oh, if you guessed at 0, 0, you guessed right. Well done. So now, before we render it, let's change its position. Let's say test dot pos dot x equals, we could make it a random position. So let's use the math library, which is already integrated into JavaScript. Let's put math.random. So that function will give you a random floating point between 0 and 1. But we want to scale that up to go across this width of the canvas. So we can say times width. The width keyword is a P5 keyword. What it does, P5, very handily. You know what, I'm going to make my canvas even smaller so that I can see it all in this zoomed in browser here. There we go. So each time we run it, we're going to get a new random point, and we're scaling it up by the width of our canvas. So as soon as we make our canvas with create canvas in P5, it stores whatever these numbers are in width and height. So let's now give it our test dot random height, or position according to the height. Right, and now it'll appear in a different place. Brilliant, simple as that. So what we also want to do is do the physics that I was describing before. So adding acceleration to the velocity and then velocity to the position. And then we want that to happen every frame. So we're going to also need like a simulation loop. So underneath my render function, I'm going to call it physics. There we go. Physics. And you might think we might do something like this. This dot velocity equals this dot acceleration. Sorry. This dot velocity plus equals this dot acceleration. Unfortunately, that wouldn't add the velocity to itself plus the acceleration, because they're not ordinary number variables. They're not floats and integers. Velocity and acceleration are vectors, and you can't just add vectors together in JavaScript using P5 like this. We've got to use a function that adds them together behind the scenes. So it's not too difficult. All we have to write is this dot vel dot add. So there's a function. And what do we want to add to the velocity? We want to add the acceleration. So this dot acceleration. There we go. We shouldn't do anything because we're not changing any acceleration. Right. Then we want to add to the position, we want to add the velocity. This dot vel. There we go. And now in render, we are drawing the particle according to its position, and the position is now being changed according to velocity. Velocity is being changed according to the acceleration. So we can add a force to it. Now, what you also want to do after you've added those two things, the velocity to the position, acceleration to the velocity, you want to zero out, multiply by 0 all the forces that you've added onto it, because next time you go around the loop, then you can reintroduce new forces. That's the way this kind of physics works. You could do it differently. You could experiment with how you're doing this for interesting effects, but I'm going to do it in the traditional way, and now say this dot acceleration. again, we can't just multiply it by 0. We have to use a vector function. So we're going to use the mult function, which stands for multiply, and we just want to multiply it by 0. So that means x acceleration is being zeroed out until we add a new acceleration to it. So let's test this out. How could we do it? What we could do is every time we click the mouse, we could accelerate the particle towards the mouse. Yeah, we could call it a suck. I don't know what to call it. We could call it a suck function or behavior. There we go, suck. And you know what? This function will actually pass in some variables. We'll pass in an x and a y, and then we could just pass in the mouse position later on. So suck, I'm going to say x and y. I just put underscores to remind me that they are the parameters. So we've got an x and a y position. So firstly, we need a direction from our particle to the target x and y. And to do that, all we have to do is take our particle's position and minus the vector position of the target. So first we need to make the x and y parameters into a vector. So let target target vector equal create vector, and then we're going to create it out of the x and the y that we've passed in. Okay, so we've got a vector, TV, and that's a target vector. So it could be anywhere on here, wherever we click. And then we want to take away that target vector from our position vector. So we need another temporary variable. We call it dv for direction. Well, actually, I'll change it to dir for direction. So a direction equals, now we need to subtract a vector from another one. So again, we can't just say the name of the vector minus the other vector. We have to use a function that will go and do it for us, because they're not ordinary numbers. So p5 provides you with a function to do that, and it's called p5.vector.sub. And then it takes two arguments. First, I think you put in the target vector. I might get this the wrong way around. We'll know if, when we click, if our particle, instead of getting sucked towards it, is like blown away from it, repulsed away from it, then I've got this the wrong way around. Anyway, let's put in TV for target vector minus the position. So the particle's position is this dot pos. And it's not dot x or dot y, because we do want to deal with the whole vector object in this case. Right, so there we go. So we've got the direction. Hopefully we've got, if I clicked up here, we've got the direction from the particle towards that point. So all we have to do now is add that direction to our acceleration. So this dot add, and we're going to put in that direction. Now, the only thing is, a vector will have a magnitude, and we want to regulate that magnitude. So before we add that there, let's just say the mag equals, or rather, let's just multiply it by, I don't know, 0.1? I think that's how I do it. I might have to use a function setMag. Let's just try multiplying it by 0.1. Let's just try that. If it has a greater magnitude, it will have a greater speed. Let's just leave it at that and see what happens. Okay, so we can now say, if we click the mouse, so let's create a new function. We're going to use the mouse pressed function. So it's outside of the class. We're now back into kind of like our main game where we've got, or simulation, where we've got the function set up. let's write function mouse pressed and create the body of the function. So this is event driven, and this is a function that P5 uses to detect when you're clicking the mouse or tapping the screen. It defaults to screen tap if you're on a touch screen. Right, so what we're going to write? Oh yes, so we're going to write test dot suck, and then we're going to pass in the mouse position. Again, P5, in its handy way, logs where the mouse is according to two keywords. That makes sense. Mouse X and mouse Y. So we should be adding that acceleration to our particle. But when I click, nothing happens. Why is nothing happening? Well, we're not using the suck function. In fact, we've only drawn our test dot once in the setup function. What we need is an animation loop, a game loop. So again, P5 has got a function for that, and it's called function draw. So you can't call any of your own functions draw, because P5 will get hold of it and run it over and over and over again. So if you write function draw, this function will be called after the setup function has run through. Then P5 will go and find draw, and it will loop it around and around. So that means in here we can say test dot no, we don't want to suck there. We want to say test dot physics. So we want to go and do its physics thing. And remember that. Where's physics? There's physics. That adds the acceleration. So if we've added a suck acceleration, that's when that's going to affect the velocity. That will affect the position of the particle, and the position of the particle is obviously used in, where is it? In render, because it renders an ellipse in its position. Okay, so in the draw loop, we're going to ask every time it goes round, update the physics of the dot, or the particle, you could call it. And then, after we've updated its physics, we then want to render it. So, if I click now, yes, the particle gets sucked towards the mouse. Okay, something happened. It moved. Now the problem is, every time we're running this loop, we're drawing just over the previous image. So at the start of our loop, let's repaint the background our lovely colour, and then we'll get the proper illusion of movement. Or will we? Oh, there we go. Yes. Okay. So now we've got a problem. It's moving kind of too fast. So let's try and set this magnitude correctly. I think it's something like this. So after we found, at least, we got this subtraction function the right way around. I didn't know if it was the TV vector first or the position vector, the target vector first or the position vector. So we got that the right way around. So that means the target vector is being subtracted from the position vector to get the direction. But now we want to set the magnitude. That means the size of our vector, because the vector that we're creating, direction, is really a vector that goes from the particle all the way to the mouse position or whatever position you've put in there. And so if it's very close together, it's going to have a tiny magnitude, a tiny size. So that will affect how fast it moves. But we want that movement to kind of be this constant. Or if we do want to change it, we want to be in more control of how it's changing. So I think you just write set mag. No, that looks wrong. Set mag. Let's just try it. Let's just put 0. I'll just put 0.1. Okay, and that's worked. So if I keep tapping or keep clicking, I can add more and more acceleration to to the particle, and now you can kind of see the effect we're after. It's like I'm creating like a gravity well where my mouse is. I keep clicking or tapping and it's working. Brilliant. So basically we need to make 100 of these particles. Let's go and do that. Right, so at the very top of the program, let's make an array, and I'll call that let dots. Okay, and to make this variable into an array, we write equals square brackets. So that tells JavaScript I would like not just a single variable here. I want this variable to have lots of spaces in it, discrete slots to put in objects or values, and we're going to put in dot objects. And by the way, I've put it in plural, dots, with an S on the end, and that's a convention in coding. If you're creating an array, you pluralize it, so it's easy to remember and easy to see that it's an array. And I just might comment that, an array. There we go. Right, so now in setup, we can go and do this kind of thing. We're going to give our dots a random position, but we're going to do it, we're going to iterate over lots and lots of dots. So I'm going to do this in a nice tidy way. Firstly, I'm going to delete our test dot. We're going to now just work with an array. Mouse pressed. I'm going to have to take that away as well. Okay. Right, let's create them there. Okay, so we're going to have a for loop for let I equals 0 while I is less than, how many dots? Oh yeah, let's have 101, and then I plus plus, and then we're going to say let new d, that's going to stand for let new dot. Sorry, that's going to stand for a new dot. That's just a temporary variable, so that we can create a new dot, store it in new d, and then push new d onto the array. I guess we could do it in a different way. We could just write dots push new dot. There we go. Yeah. Okay, so then we'd push a new dot onto the array. We do want that dot to be in a random position, I guess, do we? So what we could do is that when a particle is created, it's not created at 0, 0, but is created at a random position. So let's do that. So let's say this dot pos dot x equals, and then just as we did before, math dot random, scale it up by the width of our screen. Just trying to get everything nice and neat. There we go. Let's copy that and just change the y around and change width to height. There we go. Oh, that won't fit on the line. Damn. Okay. So now when we create all of these objects, all these dots, they're going to be at random positions on the canvas. So now in the draw loop, we just want to iterate over all the dots in a very similar kind of loop, and we just need to call each time we run through the loop the physics of each dot and to render each dot. Simple. Right. I'm going to put that straight into the draw loop, I think. I could make another function to go and do that, but it's a simple program so far. So I want for let I equals 0, and then slightly different to before, I want I less than dots dot length. There we go. So I just want to loop over the length of the array, because the length of the array is how many dots we've got. And that just means if I change this number up here, so I wanted 200 dots, I don't have to remember to change this number. It will always match, it will always dynamically change with how big the array is itself. And it also means if later on you wanted to delete dots, delete particles or add more particles, this loop will always match the length of your array. if you are removing dots, loop backwards through your array. That's just a tip. We'll talk about that another time. Anyway, I++, and then we want to run that. So we want to run dots I dot physics. There we go. And then dots I dot render. Now I think we should have our dots appearing. Okay, so something's gone wrong. Oh no, it was fine. Just taking a bit of time. So we've got lots of dots, and they're actually, the physics is ready. So we just need to add some forces. Now our tapping won't work anymore. So what we could do before we do the physics, we could add acceleration here. We could add a force here. We could say for each dot, suck towards where the mouse is. So then they're always, it's beginning to work already. They're always, because the mouse starts at 0, 0, so always going to be moving towards the mouse. So mouse X, mouse Y. There we go. Let's just have a look. Yes. So now we've got the kind of effect that's very satisfying. Oh, that's really nice. Okay, to make it more like gravity, what should really happen is the closer the particles get to the target, the stronger that attraction force could be. So really we want the magnitude of the force that we set in suck to be related to how big the magnitude is. So let's try something. That's looking very good. I definitely want my particles to be a bit smaller, I think. Although, I guess on your screen, this might look nice and clear. This is probably quite clear. Okay, so let's find suck. There he is. And, there's set magnitude. So, set strength of force. So that's what we're doing. And at the moment, we're just setting it to exactly the same. It doesn't matter how far the particle is away from the target, it's the same kind of force. Although we know we want it to be in the range of about 0.1. So we want to say set mag to its current magnitude. Now if we just set it to its current magnitude, that would do nothing. But it would mean the further away it is, the stronger it would be. So to invert that, we can write 1 divided by the direction vector's mag. And to get hold of its magnitude, you just write mag with brackets there. So now you can see, that looks really good. The closer it is, the faster the particle moves. And to get that stronger, we could up this a bit. We could say 10 divided by the direction. And so on and so forth. There we go, that's quite cool. We can also limit the speed. It could have a maximum speed. Or also we could add some friction. Although we're adding a force on, no, we won't add any friction. Well, friction would be like this. We would, after we've done the physics, we could then say, so I'm in the physics function. So after we've added the various things to various other things, I won't say that again, we could then say this dot velocity multiplied by, and we want to be very close to what it already is, because this is going to be changed every single frame. There we go. So now they kind of slow down as well. Now, depending on what kind of system you want, and I'm going to stop this video shortly, maybe you want the particles only to get attracted when they're within a certain range. So you could just ask the question in sucks. You could say, if the magnitude of, or rather the distance between the particle and the target is less than a certain number, then, you know, add the force, or vice versa, things like that. And it'd be very easy to do a repulsion force. What I'm just going to do is change the colour of the particle depending on how fast it's going. That should have a nice look. So in render, so in the class objects, in the class definition, let's go to render, and I'm just going to use the fill functions. This is a p5 function that just tells us what fill colour to use on anything that you draw onto the screen after you've used this function. And it takes three parameters like background, so red, component green, and blue. And if you just put in one number, it will, p5 will take that to mean that number for red, that number for green, that number for blue. Let's make them green. So I'm going to say 0 something 0, and I need to change this to, and let's call it G for green, and we're going to say let G equal, now we can go from 0 to 255, and we want to map that, or match the speed or the velocity of our particle. So let's say let G equal map, so this is a map function on in P5, you won't find it in vanilla JavaScript, so we're going to map to the speed of the particle, and the speed of the particle is its velocity's magnitude. Okay, and then you put the range of that, so its magnitude, so its velocity, I don't know, I think it can go from obviously 0, and let's just put 10, okay, and then you put in the range that you want G to be. So we want G to go from 0 to 255. So the faster it's going, the whiter it's going to be. Oh, sorry, the greener, the lighter the green. So now the velocity is kind of visually represented as well, which is kind of cool. There we go. They're moving quite fast for me. So I might want to slow this down. Whoa. Or let's say you only get attracted when, or rather you don't get attracted if you're too close. And we could also put a speed limiter on it by saying if your magnitude is bigger than a certain amount, like 10, make sure it only equals 10. So let's do that actually. That's a constructor, sorry. I want to find physics. There it is, there's a physics. So firstly, let's just add speed limit. So we're going to say if this velocity's magnitude is greater than, let's just try 4, then this dot vel set mag 4. Oh wow, that's having a much nicer effect overall. It's a little bit like Boyd's and following behavior. That's really nice. I don't know what noise I just made. I don't know if the mic picked up on my noise. It was kind of like a what do you call it? It's kind of like Chewbacca, but very young. A young Chewbacca is what it sounded like. Being unsure about something. Right. I think... Am I going to leave it there? Yeah, I think... I'm going to show you one thing that you can do. You could, when you draw these, or when you render them, you could add some alpha to the fill. So there's a secret fourth parameter you could put in here, and that's like how see-through the particle's going to be. So if you put just one, you'll hardly be able to see them. They're kind of invisible. The outline is visible. Let's just turn off the outline. So if you write no stroke, we're going to have no outline. Now I can just about see them. I don't know if you can see it on YouTube. But what we can then do is now turn off the background being redrawn. So every time those particles are moving, they're redrawing over and over and over the image. And if the alpha like this is very, very light, then, I'm just going to comment out background in the draw loop, then you start to build up patterns. It looks kind of blurry here, but there we go. If you experiment with that, you can create really nice kind of effects and things. Anyway, whoa. They were looking like kind of green in the middle there. That's kind of nice. Anyway, I'm going to turn that back on, and I'm going to turn on, I might leave off the stroke, but I'm going to turn up the alpha to full 255. Well, actually, let's just go halfway. Maybe 100 and half of 255. Why do the maths? Let the computer do the maths. There we go. 255 divided by 2. So semi-transparent now. And we've got a physics system. We've got some particles going on, which almost look 3D the way they move, which is kind of interesting effect. So what I suggest you might do is actually put in some real physics. Go on Wikipedia or something, and maybe put in the proper formula for gravity and things like that. Maybe you could make this look like an atom, or orbiting planets, things like that. Anyway, I hope you enjoyed that. Put any comments, any questions, that's what I'm after, any questions in the comments, and I'll try and answer them as soon as possible. Good luck with this. I hope that was useful. Goodbye.